Hello everyone. In this video, we're going to study some more examples from Chapter 5. My name is Fred Rispoli, and I'm coming to you from Stony Brook University. So we're going to discuss 3 examples on joint continuous distributions from Chapter 5. These are chosen based on some frequently asked questions by students and some previous AMS 310 tests. In our first example, suppose x and y have a joint probability density function f of xy is equal to 4xy for x between 0 and 1 and y between 0 and 1. Notice it's a good idea to try to think about what region in the plane this is. This would be the unit square. So for part A, prove that f is a valid PDF. In part B, we find the marginal PDFs. Part C, we find the expectation of x and y. And in part D, we're asked to show that x and y are independent. So for part A, we want to show that our function f of xy is a PDF. There are 2 things we need to do. We need to just demonstrate that f of xy is always greater than or equal to 0. And we need to show that the integral over our region yields a value of 1 at the end. Okay, so we know that x and y are both between 0 and 1, but in particular, if they're both positive. So when we look at the function f of xy, that will be positive as well. If we look at our double integral of our given function, so we're integrating 0 to 1, integral from 0 to 1, 4xy, we'll do dy dx. We could see that when we integrate with respect to y first, we would have 4xy squared over 2, but we could cancel out the 2, so this simplifies to 2xy squared. Y is going from 0 to 1, so we have to evaluate this integral, then integrate with respect to x. Easy to see that this simplifies to simply 2x over here. When we integrate from 0 to 1, 2x, we'll get x squared, well, 2x squared over 2. The 2's cancel, and we are left with 1. So therefore, f of xy is a PDF. Okay, in part B, we want to find the marginal PDFs. So the marginal PDF with respect to x, we integrate our given PDF. And here we're going to integrate out y. So I'm looking at the integral from 0 to 1, 4xy dy. Okay, again, so similar to what we saw before, this would be 4xy squared over 2. The 2 in the denominator cancels out. So we're left with 2xy squared, evaluating y equals 0 to 1, and it's easy to see that this simplifies to 2x. Now there's a bit of symmetry here with x and y, so it's fairly easy to see that the marginal with respect to y here should be 2y. I see this over here, except this 1 should be 2. So f2 of y would be equals 2y. Okay, in part C, we're interested in finding the expectation of x. So we could do this by integrating x times f1 of x. Right, so we're integrating the integral of x times the marginal PDF with respect to x, which we calculated up here. So our integral looks like integral from 0 to 1, x times 2x dx, so this would be 2x squared. When we integrate, we get 2x cubed over 3, evaluating where x goes from 0 to 1. Easy to see that we get 2/3 here. So this would represent the average value of x, it would be 2/3. And again, we'll take advantage of the symmetry here. The expectation of y is also 2/3. Finally, we entertain the question, are the random variables x and y independent? So what we need to do is to see if we can factor f of xy into two PDFs, or in particular the two marginal PDFs. And here you see that 4xy does in fact factor into 2x times 2y. So we have our joint PDF is in fact the product of the two marginal PDFs. So therefore we could conclude that x and y are independent. Okay, so this concludes example 1. On to example 2. So suppose that x and y are uniformly distributed over this region in the plane. Okay, we have 0 is less than x, which is less than y, which is less than 1. Okay, can you imagine this region? What does it look like? Well, the first step might be to create a graph of this. And then we're asked to find the joint probability density function and explain why it's a PDF. That's part A. And part B, once again, determine if x and y are independent. Okay, so the region in the plane would look something like this. It would be a triangle, right? So it would be a triangle with, let's think of this, this is the base. So this would have length 1, and this is the height. This would have length 1. Okay, so it's a triangle. If it were the unit triangle, right, the area would be 1, but this is sort of half of that. So that's one way to see that the area of the triangle is a half. So when we have a uniform distribution in the plane, the PDF would be 1 over the area, right? When you have a one-dimensional uniform distribution, the PDF is 1 over the length of the interval. If you have two random variables and it's uniform, you're looking for the joint PDF, the PDF is 1 over the area. So in this case, we get 1 over 1/2. So this simplifies to 2. So this is our PDF. F of xy is equal to 2. For part B, we're interested in the question, determine if x and y are independent. And to do this, well, we need to think, along a couple of different ways. We can try to factor. There's one way to factor this, or we could find the PDFs. Okay, so let's find the PDFs in this case. So my marginal PDF with respect to x is equal to the integral as x, our integral really as y goes from x to 1 of 2 dy, right? We're integrating out y, okay? 2 is our joint PDF that we found in part A. So when we find this integral, right, if we integrate it, we would have 2y evaluated as y goes from x to 1. So this simply becomes 2 times 1 minus x, where x is between 0 and 1. So that's the marginal PDF with respect to x. When we find the marginal PDF with respect to y, right? Well, now we have to integrate out x. So I have my integral from 0 to y, right? If we think up here, x varies from 0 to y, okay, of 2. Okay, that's the joint PDF dx. So this would be, when we evaluate this, we would have 2x, but x goes from 0 to y. So we would end up with 2y. where y varies from 0 to 1. Okay. Now, if we look at the product of the marginal PDFs and multiply these out, okay, we're going to have this 2 times x, 1 minus x times 2y, okay? So the 2's multiplied out give us a 4, and then I have 1 minus x times y, and that's certainly not equal to our f of xy, which is just 2. So our conclusion here is that x and y are not independent. Okay, let's take a look at example 3. Another problem from a recent test, as was example 2, by the way. So example 3, the joint density function of two continuous random variables, x and y, is given by f of xy is equal to c. Now c is some constant that we'll determine. So c xy, where x is between 0 and 2, and y is between 1 and 5, and f is equal to 0 outside of this. So what's this region? If you were to graph this, you would get some sort of rectangle. X is between 0 and 2, and y is between 1 and 5. Okay. So we're asked to determine the value of the constant c, find the probability x is between 1 and 2, and y is between 2 and 3, and then find the expectation of x. Okay, well, the idea behind part A is to evaluate the integral, find the answer in terms of c, and then set that expression equal to 1. Okay? After all, we know that we have a PDF, and when we integrate over the region, this should be equal to 1. So we set up. Let's say 1 is equal to the integral here. X goes from 0 to 2. Y goes from 1 to 5. C times xy will do dy dx. So I'm integrating with respect to y. So when I first go through here, we would have c times x times y squared over 2. Y varies from 1 to 5. Okay. Then we would have, in our second step, we would integrate that result from 0 to 2. Now we're integrating with respect to x. So I left a step out. It would be a good idea to stop the video at this point and work out this integral. Okay, great practice. And you should end up with 24c. Right? Now we think in terms of 1 is equal to 24c. So we could solve for c and get that c is equal to 1 over 24. Okay, so our complete PDF then would be 1 over 24 times x times y. Okay, so we'll use that in part B. So now in part B, we have really a straightforward probability question. Find the probability x is between 0 and 1, and y is between 2 and 3. So this is some region inside the region for which f of x and y is defined. So we could evaluate this using a double integral. So here we're going to integrate with respect to y first. So I have in my double integral, I have the integral from 1 to 2. Okay, so that's the outside integral, x going from 1 to 2. Then we have the integral y is going from 2 to 3, 1 over 24 xy. That's my PDF, my joint PDF. Integrate with respect to y first, and then x. Once again, I would suggest stop the video, work out this integral, should end up with 5 over 32, and expressed as a decimal, we get 0.15625. Okay. In part C, we're interested in finding the expectation of x. So we'll first find the marginal PDF with respect to x. Okay. So to do that, we integrate y out. Okay. So here we would have in our integral 1/24 x times y squared over 2, and then we substitute in these limits, and we should end up with 1/2 x. Okay, and again here, x is varying from 0 to 2. So now we could take this result and use it to find the expectation of x. So for this, remember when we find expectation, we integrate x times the PDF, in this case the marginal PDF with respect to x. So I have the integral from 0 to 2 x times this marginal PDF with respect to x. So we're using this function over here. So we're integrating, you can see 1/2, and it would be x squared. So when we integrate this, we'll get x cubed over 3, but with that 1/2, we'll have x cubed over 6. X goes from 0 to 2. So I have x cubed over 6. When I substitute in 2, we'll end up with 8 over 6. And simplified, we get 4/3. Okay. In our last example here, we'll take a look at another function, a little bit more complicated than the first two. Let's say we have continuous random variables, x and y. They have a joint distribution with a density function that is given by f of xy is x squared plus xy over 3. X is between 0 and 1, and y is between 0 and 2. So once again, this gives us a rectangle. Okay, find the marginal PDF with respect to y, that's part A. And the second part, so find the conditional PDF f2 of y given x. All right, so the marginal PDF with respect to y. So to find the marginal PDF with respect to y, we, by definition, integrate from 0 to infinity of our joint PDF, f of xy. So in this case, we're integrating from 0 to 1, x squared plus xy over 3 dx. So when we work this out, this becomes 1/3 x cubed, and this would become x squared y over a 2 times 3, or 1/6. X is going from 0 to 1. So you could see that we would get a 1/3 here. When x is 1, we get a 1/3. And when x is 1 here, we're left with y over 6. So that's part A. Now, for part B, we want to find this conditional. So this is sort of the marginal with respect to y given x, okay, or a conditional. And this is given by the joint PDF divided by the marginal with respect to x. So here is our joint PDF, right? This was given to us originally. And then we need to divide by this marginal PDF with respect to x. So we form this fraction, and then go ahead and do the algebra. Once again, I recommend stop the video, work out the algebra. So here, find the common denominator 3. Same thing over here, find the common denominator of 3. Put this together, you could see that you could factor out an x in the numerator, factor out an x in the denominator. That will cancel. The 3's in the denominators will cancel. We'll end up with 3x plus y. And down here in the numerator, when we multiply this by 3, we'll end up with a 6x plus 2. So you may be able to see it without, but again, a couple of basic algebraic steps will bring us to 3x plus y over 6x plus 2. Okay, and continuing with example 3, okay, suppose we're asked to first set up the integral to find the probability x is greater than 1/2 given y is greater than 1/2. So first set it up and then find the exact value, round off to 4 decimal places. All right, so we're looking for this conditional probability. Okay, so we could think of this as we find the probability x is greater than 1/2 and y is greater than 1/2, okay, divided by the probability y is greater than 1/2. Okay, so in the numerator, we're looking at the integral from 1/2 to 1, and inside is the integral from 1/2 to 2. Okay, so this is our joint PDF, and you can see that out here I see we're missing how we would integrate this, but this would be integrating with respect to y first. So this inside integral is with respect to y, and then we integrate with respect to x. So when we work this out, we end up with 43 over 64. And then when we work out the denominator, right, so now we're going 1/2 to 2. But here, notice that we are using the marginal PDF with respect to y down here. So I have integral from 1/2 to 2, 1/3 plus y over 6 dy. You may remember that we got this right here in part A. This is the marginal PDF with respect to y, so we're using that down here. So that works out to be 13 over 16. And we could simplify this fraction a little bit. We get 43 over 52, which works out to 0.8269. So I'd recommend, once again, perhaps stopping the video, try to work some of these problems out, and then take a look at the solutions. So that completes the video. I hope you found it helpful.